So, my name is Daryl Fisher, and in this presentation, I'm going to be doing a regression analysis of wild-type blue jay mass. So the data set I found concerns the masses of wild-type blue jays and their other phenotypical measurements such as beak dimensions and skull dimensions. So the original goal of this data set was to collect data to find the average phenotype of wild-type blue jays, and to find the differences between male and female jays. They utilized simple correlation and comparison, so there's no regression techniques involved. The data was collected from Keith Tarvin at Oberlin College, and it was uploaded to the Stat2 data package in R after the results were used in the article listed about blue jays. And in the Stat2 data package, it has the title Blue Jays. It contains 123 data points from 123 unique blue jays, and they were marked after capture and measurement so they could tell if they had been measured before, so essentially each jay was randomly selected and independent from the others. My research question for this analysis was how do easily measurable phenotypical differences in blue jays, such as their bill length or their skull diameter, affect its mass, which is my y variable. And so all of my hypotheses are one-sided hypotheses, and so my null hypotheses, all collected together, would be that the thickness of the bill, the width of the bill, the length of the bill, the distance from the tip of the bill to the back of the head, the distance from the base of the bill to the back of the head, and being male will all have negative or no impact on the mass. Those are my null hypotheses, and that would mean that all of my beta parameters would be less than or equal to 0. Whereas my alternative hypotheses would be that the thickness of the bill, the width of the bill, the length of the bill, the distance from the tip of the bill to the back of the head, and the distance from the base of the bill to the back of the head, as well as being male, would all have positive impacts on the mass, so all of my beta parameters would have to be positive. And we are going to perform k-fold cross-validation in order to confirm our model. That's part of my hypothesis. So our y variable here is our body mass, which is measured in grams. Our x1 variable is the thickness of the bill measured at the nostril, which is measured in millimeters. Our width of the bill is our x2 variable, which is also measured in millimeters. Our x3 variable is the length of the bill, measured in millimeters. Our x4 variable is the distance from the tip of the bill to the back of the skull, which is measured in millimeters. Our x5 variable is the distance from the base of the bill to the back of the skull, which is measured in millimeters. And our x6 variable is the sex. It has two levels, 1 if it's a male, 0 if it's a female, and it has no units. So our sample size is 123, and then there's no data screening was necessary because there was an appropriate amount of data points and variables, and all of the data points were already independent. So for the preliminary analysis, I performed a first-order linear regression model with all of my independent variables, x1 through x6, which returns the model listed here. The summary and ANOVA table are displayed to the side. Some highlights of that are that the r-squared is about 0.49, and that x1, x2, x3, and x4 are all significant under the f-test. So for the diagnostics on that first-order linear model, I performed a Brown-Forsythe test with 5 groups and received a p-value of about 0.92, which indicates that we shouldn't reject the null hypothesis. There's no evidence of non-constant variance. I then performed a Shapiro-Wilk test. I received a p-value of about 0.13, which indicates we shouldn't reject the null hypothesis. There's no evidence of non-normal error terms. Our normal probability plot is linear, so that confirms the Shapiro-Wilk test, and our residual plot shown there, it looks pretty linear from that residual plot, and it also looks like the residuals are scattered randomly with no evidence of non-constant variance or non-normal parameters. And so the next thing I did was I plotted the added variable plots. And based on this, it looks like the data is linear, although it is clumped for x3, x4, and x5. X2 looks like it has the least impact on y, but all of the other ones look pretty relevant. So this clumped data might be an issue, so the data outside the clusters might be x outliers. So that's what I decided to analyze next. So for the outliers, I recorded the x outliers via the HAP matrix, the y outliers via the studentized residuals, and then influential points via dfits, df betas, and Cook's distance. So we did have 10 outliers via the HAP matrix outliers, which are highlighted in yellow, and we did have one white outlier, data point 26, also highlighted in yellow. From dfits and df betas, we had a lot of influential points, actually. Those aren't listed here except for dfits. But via the Cook's distance, we actually didn't have any influential points, even when we lowered the critical value to f of 0.27116 from that higher mark of f of 0.57116. And so from that, we can conclude that there are no substantial outliers, primarily based on that Cook's distance, no influential points measurement. The next thing I did was analyze the multicollinearity, which I thought would be a really big issue because bigger birds are going to tend to be bigger in all regards, not just in 1 or 2 dimensions. And so the fit values for single regression for all variables was acceptable, but for double regression, it was acceptable only for most combinations. But it was not acceptable for 3 on 4 and 5, 4 on 3 and 5, and 5 on 3 and 4, which we can see from the scatterplot matrix here. We see a really high degree of multicollinearity in this variable. And so because of that, I think the best way to move forward is to remove one of these variables or to attempt a ridge regression. So just to summarize the diagnostics on the first order model, our linearity condition is met, there are normally distributed residuals, we do have constant variance of the residuals, there are no major influential outliers via the Cook's distance, but we do have a multicollinearity issue, as determined by VIF, the correlation values, and the scatter plot matrix. And so there are two ways to proceed. We could do a ridge regression, or we could do a best subsets analysis. And so I'm going to choose to do a best subsets analysis because it makes sense that there's a lot of variables related to each other in this model, and by removing one or more of those interconnected variables, we could reduce the multicollinearity to a point where the ridge regression might not be needed. And so from the best subsets analysis, we've got highlighted the best selection method for each predictor, and the best model for the most selection methods is the one with 5 predictors, so that's x1, x3, x5, and x6. It has the most predictive power because PRESS-P and CP and AICP, they tend to pick better predictive models. And it also likely gets rid of the multicollinearity issue because x4 is removed, which is one of the 3 variables which, when combined with x3 and x5, was causing a lot of issues. So therefore, I select the model y hat is equal to beta naught plus beta 1 x1 plus beta 3 x3 plus beta 5 x5 plus beta 6 x6. So this is just a summary of the best subsets model. We've got an R squared slightly lower at about 0.479, and we've got x1, x3, and x5 all significant under the F-test. So to diagnose that best subsets model, I performed a Braun-Forsythe test with 5 groups and received a p-value of about 0.89, which indicates that we shouldn't reject the null hypothesis. There's no evidence of non-constant variance. The Shapiro-Wilk test gave me a p-value of 0.15, which indicates we shouldn't reject the null hypothesis. There's no evidence of non-normal error terms, which we can also see in the normal probability plot there, which looks linear. From the residual plot, we can see that the data still looks linear. We've still got approximately non-constant variance, normal residuals. All of that looks pretty good. The added variable plots, it looks like the clumping from the earlier regression is pretty much gone now, which is good. And it also looks like the data is still linear here, the clumping is gone, data is more spread out, and it looks like all of the variables are relevant to the model. x1, x3, x5 all have a positive relationship on y, and x6 has a negative relationship. From the outliers, I performed the same analysis as before. For x outliers, we didn't have any. We had one y outlier, still data point 26, as before. DFITs returned a couple of different influential points. DF betas did as well, but Cook's distance still didn't, even with a probability of 0.2 instead of 0.5, and so because of that, we can conclude no substantial outliers based primarily on Cook's distance. And now to talk about that multicollinearity issue again. So the VIF values for single regression for all variables is acceptable still. For double regression, it is also acceptable. And for one variable and all other variables, it's still acceptable. So that's really good. So there's no excessive degree of multicollinearity based on the VIF of the R values. The scatter plot for bill depth and bill length does indicate some correlation, but it doesn't appear overly problematic according to VIF. Our correlation values there also don't appear to be too problematic. And so just for a quick summary, our linearity condition is met, our normally distributed residuals condition is met, our constant variance condition is met, our no major influential outliers condition is met, and the no multicollinearity condition is met, but it could be improved. And so what I think we should do from here is proceed with a ridge regression to complete the analysis. So to choose our value of lambda, I did a ridge trace plot, I did a cross-validation with GVC, and I also decided to look for the closest VIF to 1. And so I chose to use lambda as 0.03 based on the press values for each lambda because I wanted the most predictive value. I just chose the smallest press value out of the 3 I tested. That gave me the smallest GVC, the minimum MSE, and the VIF closest to 1. So from that ridge regression right there, with a lambda of 0.03, we get y is the formula that's listed here. The AIC and BIC are pretty low comparatively. The parameter estimates are pretty reasonable and relatively stable, so this seems like a good path to go along. So now I just wanted to do a quick diagnostic on the ridge regression. I performed a Braun-Forsythe test, got a p-value of about 0.9, which indicates that we shouldn't reject the null hypothesis. There's no evidence of non-constant variance. The Shapiro-Wilk test returned a value of 0.18, which indicates we shouldn't reject the null hypothesis, and there's no evidence of non-normal error terms. Our normal probability plot is linear, which also confirms that, and for our residual plots, the normal and constant variance assumptions were upheld, and it's likely linear as well due to the residual plot. The added variable plots aren't really necessary to determine linearity since we already know this from the best subsets model. As for the outliers, finding outliers for a ridge regression is actually really mathematically complicated and it's not covered in this course. So we can assume because the best subsets model is very similar to the ridge regression and there are no major outliers and influential points on the best subsets model, there's probably none on the ridge regression as well. As for the multicollinearity issue, the scatterplot matrix and the correlation values are going to be identical to the best subsets because they don't consider the fitted values for the regression. But we know that VIF is between 1 and 2 since we chose the parameter lambda to reduce the fifth value, which is less than the best subsets model, so it shows improvement in multicollinearity. And we also know that this model is a better predictor of y since its press value is smaller than the press value for the best subsets model. So just to quickly summarize, our linearity, normally distributed residuals, constant variance on the residuals, no major outliers, and no multicollinearity conditions are all met and improved from the best subsets model. So we've already performed a cross-validation on lambda when we chose what value it should take, so the only thing left to do is to perform a cross-validation on the best subsets model. So we had 4 models considered under the best subsets analysis. The first one has all of the variables, and it had a root MSE of about 3.44 from 10-fold cross-validation. The second model we considered had 5 predictors, x1, x3, x4, x5, x6, and it had a root mean squared error of about 3.46. The third model that we considered was the one that we ended up choosing, and that had a root mean squared error of about 3.43. And the final one had 3 predictors, x1, x3, x5, with a root mean squared error of about 3.48. So based on this, our model is the correct model because it has the lowest root mean squared error of all the models we considered. And then we could go from there and apply a remedy measure to reduce the effects of multicollinearity. And so finally, we want to discuss and conclude. Our final model is what's listed there with variables x1, x3, x5, and x6. We concluded that that was the best model by finding the first order model with all the variables and discovering that all of the conditions were met except no multicollinearity. So we didn't have a transformation of x or y because we didn't have to improve linearity or the residual assumptions. We didn't have to consider higher orders of interaction since the data was already linear, and removing outliers was also unnecessary because there were no major influential points. We proceeded to use a best subsets analysis to narrow down the number of predictors to try to get rid of those multicollinear predictors. So most of the selection methods chose the model y goes as x1 plus x3 plus x5 plus x6, and we ended up picking this model. All assumptions were met on this model, but there were some still possible mild multicollinearity issues, so we performed just a ridge regression. We didn't have to perform a robust or a weighted least squares because those weren't issues that we were having in our model. And so we performed a ridge regression with a cross-validated value of 0.03 for lambda, which resulted in our final model, and we confirmed that via 10-fold cross-validation as well as our cross-validation for the lambda value. So for our hypothesis tests, I bootstrapped a 90% confidence interval for each beta parameter, but since our hypothesis tests are one-sided, we're only going to use the lower bound to test our hypotheses at alpha 0.05. And so for our first hypothesis, since our lower confidence interval bound is greater than 0, it's not contained within the interval, so we can reject the null hypothesis, and we have evidence that the thickness of the bill has a positive impact on mass. Now, for the second hypothesis, since x2 was dropped from our model, we can reject the null hypothesis, and we have no evidence to suggest that the width of the bill has a positive impact on mass. For our third hypothesis, since our lower confidence interval bound is greater than 0, 0 isn't contained within the interval, so we can reject the null hypothesis, we do have evidence that the length of the bill has a positive impact on mass. For our fourth hypothesis test, since we dropped x4 from the model, we can reject the null hypothesis, and we don't have any evidence to suggest that the width of the bill has a positive impact on the mass. For our fifth hypothesis, since our lower confidence interval bound for the x5 is greater than 0, 0 isn't contained within the one-sided confidence interval, so we can reject the null hypothesis, so we have evidence to suggest that the distance from the base of the bill to the back of the skull has a positive impact on mass. And so finally, for our sixth hypothesis, since our lower confidence interval bound for x6 is negative, 0 is contained within the one-sided confidence interval, so we fail to reject the null hypothesis, and we have no evidence to suggest that being male has a positive impact on mass. So we do have a couple of limits on our results. First, that our data was collected close to Oberlin College in Oberlin, Ohio, so different populations of blue jays, such as southern versus northern, may have different relationships between mass and beacon head measurements. The data was also collected in 2008, so ecological changes such as deforestation and climate change may affect the relationships explored in this dataset as those populations evolve. The data doesn't include non-mature blue jays, so it shouldn't be used to predict the masses of juvenile birds. And finally, data doesn't specify the season in which the measurements were collected, and so birds might be heavier in seasons where food is more abundant, so the seasonal effects are really unknown in this dataset. So finally, to answer our research question, how do easily measurable phenotypical differences in blue jays such as bill length or skull diameter affect its mass? Our hypothesis tests tell us that bill length, skull length, and bill depth have a positive relationship with mass, and that being male does negatively impact the mass, which I didn't really initially expect. The bill width and the head length are not related to the mass according to our hypothesis tests. Therefore, ornithologists or hobby birdwatchers could expect a blue jay's mass using that model that we found instead of having to mass the bird in the field. This also has implications for pictorial analysis of blue jays and predicting the mass from length measurements from pictures. This could be used to assess the ecological success of the species in different areas without a large-scale and intrusive data collection procedure. However, the model should be limited to the Midwestern United States and only used on adult blue jays due to the limitation of the data collection. It may also not be completely correct due to evolving populations and seasonal effects. In the future, we can consider more parameters like wingspan or consider seasonal effects on mass and try to update the data to current times in 2021. So just to compare what we did with what the original dataset was used for, the original dataset was used to basically collect summary statistics on the population of blue jays in Ohio. And it really only used simple comparison to compare male and females. So the pros of this is that it's easy and simple to understand for all levels of education, and it provides more information about averages rather than relationships. However, the cons of this are that basically regression just provides more information about how variables affect others. It's more sophisticated and it provides more precision to the results, and we can actually use our model to make predictions in the future, whereas just the simple relationship effects can't really be used to do that.